so, so that it will actually get all recorded. Um, but yeah, so I'm for some reason I'm being kind of disorganized this week. I was in lab last night and I packed up all my book and stuff like that, my computer and all, and somehow managed to walk out the door of the lab without my reading glasses. And got home and I'm like tearing everything apart, going, "Where are my glasses?" And suddenly realized that I had probably left them at work. So that was my first chore of the morning, was to drive back over to the Norfolk campus and go get my glasses, which made me feel really dumb. All right, questions on solutions, topics, or homework that should be turned in later tonight? Hopefully we're fairly straight on that. All right, we are going to switch gears and talk about kinetics. Kinetics is really kind of different than what we have been doing, in that, yes, there are still equations for reactions, but that's not actually the primary focus of having a reaction take place. So for kinetics, what we're looking at is rate that it happens. Okay. Meaning that, is this kind of like an acid rain reaction where, yes, we have acid rain hitting the Parthenon in Greece, which is damaging it, but it's only damaging it, over a span of years, as the sulfuric acid in the rain begins to eat away at the limestone. So really slow reaction at that point. There are other reactions where you just dump the two things together in a beaker, like the precipitation reactions from last semester, and in a second or two, it either precipitates or it doesn't. And so those are kind of either end of the spectrum there for really slow versus relatively fast. What we're going to be looking at in terms of rate is two separate parts here. We've got changes in concentration. So delta, the little triangle, is your change in symbol. And you will see pretty much through the rest of the semester that anything written in square brackets is designed to be interpreted as a molarity. So there's a little note down there, a couple lines down, to remind you that the square brackets mean that. We're also going to have it as change in time. Now, time can be measured a whole bunch of different ways. If we look at my first example graph here, this one's got time being measured in hours, H for hours. I don't know why they didn't HR for hours, but for some reason it's just H. We're looking at hydrogen peroxide decomposition, because hydrogen peroxide falls apart. Yes, if you pour it on the cuts on your skin, or if you swish it around your mouth to disinfect your mouth after dental work, yes, that also causes decomposition. But hydrogen peroxide is not super stable. The reason they sell it in brown bottles at the pharmacy or the grocery store is because protecting it from light lowers the speed at which it falls apart. Hydrogen peroxide falls apart into water and oxygen gas, and it does so all by itself. So look at the graph there. We've got concentration going up the side. We've got time going across the bottom. This particular graph has a little tangent line drawn there. And I've spent way too much time doing calculus and physics with my big kid lately to make me think about the fact that when you're doing derivatives, I believe it is, the place where the straight line touches the curve is usually relevant when you're doing that. We're more interested in kind of broad stroke interpretations. Looking at this graph, we see that, yeah, okay, there's a straight line at that one particular point, but if you look at the graph overall, it's a curve. You have this long, gentle curve that in this case started out at 1 molar. And over a span of hours, basically over a span of about a day, approaches 0 in terms of its concentration. From a realistic point of view, you're probably going to get what they call an asymptotic approach to 0, meaning that there's a chance that you're never going to get all absolutely 100% of those molecules to convert over to water and hydrogen gas. There's always a chance that 1 or 2 in an entire beaker full might not decompose. So this is why we sometimes claim that it's approaching 0, but may not become exactly 0 at a later point in time. So let's look at some more number values here. This is data that I stole from a textbook. We're looking at time as your left-hand column there, and then peroxide concentration in square brackets, so molarity there as your right-hand column. And yeah, that's a really flaky time unit, 2.16 times 10 to the 4th. However, think for a moment. So 2.16 times 2 is 4.32. 2.16 times 3 gives you 6.48. So basically, what we're doing is we're using the same aliquot, the same bunch of time, but we're following it at that pace as it goes. So in the beginning, when I first poured the stuff in the beaker, I had 1 molar. So at about 6 hours later, so 2.16 times 10 to the 4th seconds, it's diminished to about a half. Okay, same time aliquot. Again, note I'm halving again from 0.5 down to 0.25, and we kind of continue on that process. So we went 1/2, quarter, 0.125 is an eighth, 0.0625 is a 16th. So if we, and I didn't really have enough room to do this all horizontally, so that's why there's kind of a second layer of data here. If I look at the change, well, the changes actually mirror the same data that I had above. I just didn't include the 1 because the 1 started out at 1. Also note, I have 4 lines of data instead of 5 lines of data because I didn't include the very first line. That was my starting point. So I've got my data there of change, 0.5, 0.25, 0.125, 0.0625. I have the same time unit, my wonky 2.16 times 10 to the fourth seconds. So if I divide the left-hand column that has my little change symbol above it, divided by my consistent time unit, look at your rate. And you can even kind of guess that from the graph, because it started out relatively fast and then dropped down to kind of middling in its rate. And the further out you got in time, the more and more sluggish it gets. So that my final calculation here is 0.29 times 10 to the negative fifth. So one of the reasons for kind of looking at this data is to give you both a graph and some data to reinforce the idea that rates of reactions are generally not a constant number, which is kind of the starting point for kinetics. So here's some reasons. Okay, when you're back at the beginning of your reaction, okay, you have a beaker full of molecules. So since they have to hit each other to react, if you have lots and lots, a mole's worth or more, when there are lots of reactions, or there are lots of molecules available to make the reaction happen, you get a fast rate. Well, once they get used up, okay, you have less and less and less available. And this is part of why your rate is slowing down. Well, because we have this change, okay, your rate was fast in the beginning and slow at the end. Average rate, while somewhat useful, is probably not as useful as it could be. So now we begin to get into rate versus concentration. Okay, same reaction. We've got hydrogen peroxide. The implication here is that they were using a spec 20 probably, since it says 445 nanometers as what they're analyzing at. So they're probably doing this with some sort of color added so that it changes with time. And you get a straight line because it's not concentration versus time, it's rate versus concentration. Now, this is a different way to interpret data, and this heads us in the direction toward a lab that we actually are going to do as a simulation this semester. I actually need to find out from Mr. Wheaton and Dr. McHugh, because there's one ingredient. Most of the ingredients we keep in stock in the back, and there's one ingredient that has to be mixed usually the day we do it. And I would really like to film a video of the reactions so that they can be part of the simulation. So I need to find out from my colleagues whether or not there is a plan for more than just me to do this, because sometimes I do things that other people don't do the same way. So stay tuned for that part. There may be possibly an upcoming video that corresponds with the kinetics lab. So don't know for sure yet. But looking at the data here though, okay, obviously they had imperfect data, because if you squint a little bit and you see where the dots are, and the first way they graphed this was connect the dots. So it's not quite exactly a straight line, but then you can see from the equation printed there that they went back and did a trend line. And gave the equation. Your R squared value is actually pretty good too. Remember that the closer you are to 1.0, the better your data is. And they've got 0.9987. So this is pretty decent data. Not perfect, but definitely pretty good. We're going to be using these ideas as far as kinetics go to help you calculate kinetics for a particular reaction. Since some people did actually do lab with me yesterday and some people will do lab with me on next Wednesday, we're going to do trend line graphing for Clausius-Clapeyron data. Yes, if you talk to people who did lab yesterday, you get to see water cool, which is kind of vaguely excruciating, but on the other hand, it gives us good data for our trapped air bubble. So we need to address some things that affect rates of reaction. One of those is literally what it is, okay? The textbooks usually refer to it as nature of reactant. So if we look at a couple of small metals, small not transition metals, we've got some calcium and some sodium. If you put sodium water reaction in your search bar for YouTube, one of the search hits there involves two young guys and a galvanized metal tub on the front lawn of what probably looks like their frat house, and heaving a giant chunk of pure sodium, where they got it, I have no idea, into this giant steel tub, and it kind of goes kablooey, okay? Because sodium and water is a fairly epic reaction. Sometimes I do this back when we have lectures in person. Sometimes I have done this as a class demo. We keep a small amount of pure sodium stored in kerosene in our stock room and can cut off a small slice for the purpose of demos. And it makes little poppy sounds, and a lot of times you get this little tiny like spurt of flame that's about, half an inch high, as it fizzes away into nothing in the reaction. Calcium has the same basic reaction in that it does react with water, it does make hydrogen gas, and it does give you a metal hydroxide. But calcium looks kind of more like an Alka-Seltzer. It just sits there and froths. So almost identical reactions, almost identical products, the metal being the only difference there. But there's a pretty big difference in the rate. Surface area also affects your rate. If you took a strip of zinc, nice, like maybe centimeter wide, 2 or 3 centimeters long, and put it in a hydrochloric acid solution, again, kind of like the Alka-Seltzer, it'll sit there and fizz because it does produce hydrogen gas and zinc chloride. But if you would like a much faster, much more fun to watch reaction, you could take powdered zinc, which has much more surface area, and put it in your hydrochloric acid, and it will froth, okay? Because it's going to give you better rate due to the greater surface area. If you have a fish tank that has not the under gravel filters, but the kind of old school activated charcoal in the little funny bag that fits along the back of your fish tank, activated charcoal is not quite exactly powdered, but it is relatively finely granulated so that the charcoal can help remove the ammonia from your fish tank. You can get the same reaction with a piece of coal, okay? However, since fish poop, pee pretty continuously in the fish tank, your fish tank might end up being pretty bleh, because the charcoal would not remove the ammonia at the same speed due to the lower surface area. How about temperature? Okay. One, we can start with a generalization. Higher temperature gives you faster rate. Okay, that's just kind of a general statement. We can also approximate within certain constraints that lots of reactions will double their rate for roughly every 10 degrees Celsius increase. Now note your constraint here. We have an EA is known as activation energy, and we'll come back to that later, needs to be not real huge. Okay, now think about this. Think about the whole temperature and faster rate thing. So if you buy a gallon of milk, obviously in the US, we pretty much all store our milk in the fridge, okay, which has a temperature of about 40-ish, not 40 Fahrenheit, so about 5 Celsius. And your gallon of milk, typically speaking, depending upon how fast you actually use it, probably lasts somewhere between about a week and a half before you reach the chunky phase, okay? Because protein decomposition does eventually happen. On the other hand, some parts of Europe don't necessarily refrigerate their milk because they tend to buy smaller quantities and they buy it more frequently. But think about this. If you left your gallon of milk not in the fridge, if you left it out on the countertop, you might get 2 days before it's just absolutely gross. Okay? So the higher temperature definitely influences the rate at which the decomposition happens. Concentration also affects. This is an independent variable from the temperature. Yes, it is possible to change both concentration and temperature at the same time, but then you're not controlling one variable if you do that. When we run the Bunsen burners in the lab, the little rotating lower edge, which allows you to have a nice blue flame, a nice well aerated flame, gives you a ratio of about 20% oxygen to your methane, which is the natural gas, which makes your Bunsen burner go. However, natural gas in the presence of pure oxygen burns so much faster. So let me tell you a little tale. Purdue University, I believe it is, has a tradition in their engineering department that involves a grill and charcoal and how fast you can get your charcoal lit and going. So people over the years have used a batch of different methods, everything from like electronic ignition starters to all sorts of different types of lighter fluids to try to speed things up or control the burn and all sorts of things like that. So LOX, not the kind you put on your bagel, okay? LOX meaning liquid oxygen. One year, one of the teams acquired a liquid oxygen source. Now, liquid oxygen, like liquid hydrogen, is incredibly cold, but it's also incredibly pure. And they had a bucket on a very long pole and poured it out of the Dewar flask into the bucket and put their ignition source on top of their charcoal and poured the liquid oxygen on it. One, they won the competition. Okay, it was like 0.67 seconds. Okay, there is another problem though. The grill was a puddle on the concrete. So kind of a little bit of a tale and a little bit of amusement factor there. In terms of concentration makes a difference. Okay, having pure oxygen makes a really big difference, especially in combustion reactions. Now, the last of the variables that we deal with is a catalyst. And we're going to mention it a little bit here, and then we're going to kind of circle back to catalysts again later in the chapter. Now, things that are true about catalysts, they have the peculiar property of not being used up themselves. Okay, kind of approach the idea this way. You have a swimming pool full of water that you want to bail out for whatever reason, and somebody gives you a bucket. Okay, granted, it's slow, okay, but you can use the bucket again and again and again and again to work on bailing out that swimming pool. And that's kind of how the enzyme works. It's a way of taking an item, also known as a substrate, and plugging it into a catalyst. And one, making the reaction go faster, but also then being able to use the catalyst again. There are many things, many reactions, especially biochemical reactions, where enzymes make things go much faster. Again, this is something I'm going to mention again later. Think about your DNA. Okay, everybody's had at least a little high school biology. A's and T's and G's and C's, the things that make up your DNA. Well, if you have one strand as a template, you could drop that one strand in a beaker full of A's and T's and G's and C's, and it would self-assemble. It would match things up, because remember, intermolecular forces, and you would eventually get double-stranded DNA out of it, but it would take about 6 or 7 days for that to happen. Okay, if you cut your finger on a paper, okay, or a knife or something, you don't want to wait 6 or 7 days for your cells to produce one new copy of DNA one time. Okay, DNA enzymes, specifically DNA POL1, okay, DNA POL1, is one of the key enzymes in the process. And you can get replication of your entire genome in about 90 minutes. So comparatively speaking, that is way faster. So as we progress through this, we're going to kind of adopt some profiles for how we deal with some of this information. You will sometimes see it written where K is rate divided by your reactant concentration and it's written in that direction. However, the lower one there, rate equals K times reactant concentration to an exponent, is actually the one that you will see much more of. This is sometimes referred to as a rate law. So let's look kind of at the pieces here. So a rate itself, okay, we saw rate at the beginning of the chapter. Rate itself is how much did you change over how much time? Molarity per hour was the one we were looking at on the graph there at the beginning of the chapter. The K is a rate constant. Every reaction has a rate constant, and we'll kind of circle back to this a little bit more later. Rate constants also change with temperature. Your square bracketed reactant concentration may also be raised to a power. Now, there are a limited number of options there. As we proceed, you will see that the options that are available for that little n value are 0, 1, 2, and 3. Okay, no negative numbers. And for purposes of general chem, there is nothing above a 3 that would likely to be put in that spot. All of this is actually determined in the lab, okay? It's experimental data that actually allows you to figure out what kind of values need to go in this rate equation. So we start this idea with the idea that there's two different variants on this. And no, you're not going to have to do the calculus, but know that it does influence how the equations were set up. We're going to approach this from an algebraic point of view, but it was differentiated or integrated in order to produce some of these particular equations. So the differential one is primarily a comparison between rate and concentration. The integrated ones take that concentration and compare it to time. So what can I do with this? If we look at this kind of goes back to the ones we were looking at earlier of graphing rate versus concentration. One of the things we saw earlier was that actually gives me a straight line, given the limits of experimental data. It'll be pretty close to a straight line, which you can trend line, versus the concentration versus time one, which there at the beginning of the chapter, we saw that long, slow, decelerating curve that happens when you're doing that. So if we approach this from kind of a theoretical point of view to start with, sometimes you have two reactants, sometimes you have two products. Not always. Sometimes you might have two products and one reactant, or reverse, you might have two reactants and one product. It kind of varies a little bit. When you write your rate law, they all kind of resemble each other. It's kind of like when you do algebra. Algebra, it's y equals mx plus b. That's your straight line thing. The same idea kind of goes behind this. So the rate is on the left-hand side of the equals. You've got your K value. And if you happen to have two reactants, or technically three, they are put in the square brackets with appropriate exponents. and your textbook doesn't agree exactly with your lab book on this. This is why I kind of mentioned this. The textbook, I think it's this textbook. I've switched textbooks so many times. Every time I switch textbooks, it's like, which one does this use? But you may see M's and N's used as the little exponent symbols instead of lowercase a and lowercase b. Doesn't change the math. It's just the letter of the alphabet that they happen to choose for their examples. So how do you figure this out? Also note, yeah, I had C's and D's. What happened to them? They don't get used for kinetics. They'll get used when we get to equilibrium. But for kinetics problems, you're really only paying attention to the reactance side. So how do you figure out your exponents? This is when you need the data, okay? And most textbook stuff will give you a chart because the data may or may not support the coefficients that appear to be in your reaction. Okay, so look at my reaction here. According to this reaction, I have 1 nitrous oxide, NO, and 1 O3. And I get products, which actually aren't terribly relevant, but are NO2 and oxygen molecule. Basically, I swapped one of my oxygen atoms from one molecule to the other one, and that was kind of the goal of the reaction there. So my rate law, like I said, they all kind of look the same. I've got rate equals K, NO to the something, and O3 to the something. I just don't know what those somethings are yet. Start looking at your data. So let's look at the first 3 lines there. So in the first 3 lines, note, I am holding my NO concentration fixed. All of them say 1 times 10 to the negative 6th. But I am changing one of my reactants. 3 to the negative 6th, 6, 9. Basically, I doubled it and then I tripled it. And then I look at my rate. So when I changed something, what happened to the rate? It is a comparison. So let's look at the first 2 lines of that block there. When I go from 3 to the negative 6th to 6 to the negative 6th, that's a doubled concentration. My rate doubled too. 0.66 times 2 gives me 1.32. Now, granted, both of them are to the negative 4th power. And so what this tells me is that for my O3 molecule, it does actually have a coefficient of 1. All right, let me stop and see if I can do this on my whiteboard. All right, so think about it this way. If I have 2 to the 0 power, okay, we're back to like basic rules of algebra here. So 2 to the 0 power is 1. So if I had a 0 exponent, I would not have seen any change in my rate. And yes, this does occasionally happen. When I have 2 to the 1st power, okay, 2 to the 1st power is 2, which is actually what was happening there in that first 3-line block. I doubled my O3, and my rate doubled. So 2 to the 1 gives you rate. You can figure out, like, this is your exponent here, and then this part over here is what happens to your rate. We will eventually also see that sometimes if you have 2 squared, if you looked at your rate, you would see that your rate actually goes up by 4. Okay, so kind of keep that in mind as we're looking at some additional data here. All right, let me flip back to my kinetics file. All right, let's look at the second 3-line chunk. Since good rules of science say only change one variable at a time, the second 3 lines involve changing my NO, but keeping my O3 molecule fixed. In this case, it happens to be 9 times 10 to the negative 6th. And I did a similar thing to my NO that I did in the 3 lines above. First, I doubled it, then I tripled it to kind of see what that did for the rate. So if we look at the first 2 lines, my highlighter, let me do this. Yeah, not too bad. Okay, so look at your first 2 lines there. I doubled my NO. Okay, ignore the O3 because it didn't change. I doubled my rate. 1.98 times 2 gives you 3.96. And so I have a similar performance here. Doubling the concentration doubles my rate. So this also means that my NO has an exponent of 1. And remember that in all rules of algebra say 1s are not shown. They are implied. So in this case, my equation did actually match my data. Sometimes it does, sometimes it doesn't. So I can state some certain things here. I can say that since my A, basically my little exponent above the NO, and my B, the little exponent above the O3 molecule, each happen to be 1, you can say that my reaction is first order in NO and first order in O3, which would actually make my whole reaction start to finish second order because you get to add your exponents. But I also might need to solve for my K value. Pick a line of data. It doesn't actually really matter which line because the data for this particular example is relatively perfect data. There's no particular glitches in it. So if I want to figure out what my K value is, so I picked like the 3rd line of the top chunk. My rate was 1.98 times 10 to the negative 4th. Each of my concentrations had a known value, 1 times 10 to the negative 6th and 9 times 10 to the 6th. Crunchy, 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 the math. Finish your division. And we get 2.2 times 10 to the 7th. One of the things you need to kind of just keep in mind as an overview is K's can be quite variable. Some K's are enormous. In this case, we've got something to the 7th power. decays are also capable of being really pretty small. So unlike some other things we looked at in solutions and a little bit in intermolecular forces, I don't have a recommendation for you on when to go, oh no, that number can't possibly be right. This one is definitely less clear cut. You just have to keep track of all your exponents and try to be a little on the meticulous side for your exponents. I can't give you an idea that if it's over this, it's too big, or if it's under this, it's too small, because it really is variable. So let me talk about, go back through this bottom bit here. So coefficients are not always 1. Like I said, your options are 0, 1, 2, 3. If they are 1, the wording that goes with this is just say that it is first order. So like I said, in this case, my NO is first order and my O3 is first order. And then you can add them together to give you second order for the entire reaction. So I am going to stop that and switch gears to a lab thing for a few minutes. If I can find the file, this may take me a minute. All right, I think I got the right file. All right. These are my notes, okay, which don't exactly correspond with what's on Canvas, but they're mostly the same. So some people have already done the lab. Some people are going to do the lab. Let me talk about the math here, because the math is not easy, okay? It's algebra, but it's messy. So in this case, since some of you have already done this, and you can, those who haven't done it, you can go back and look at the pictures that are in the file that's loaded to Canvas. You have this upside down graduated cylinder. It's one of the shrimpy ones. It only holds 10 mils. You have this air bubble. So typically when it's at room temperature, if you have it set up correctly, your air bubble is kind of between about 3 and 4 mils in its size. You have to have an H value that you measure with a ruler, okay, because it's in millimeters. And what you do is you sort of hold the ruler up to the beaker in which your upside down graduated cylinder is submerged, and you measure this, and typically your H values tend to be 40 millimeters, 50 millimeters, somewhere in that ballpark. And I did make a slight change here. The people who did it yesterday, we actually did 6 readings plus the 5 degrees Celsius one. All right. Why does this work? Okay. The little bubble inside your graduated cylinder is actually a mixture of dry air and water vapor, because it is actually submerged upside down in water. And so we're going to set some things equal to each other. We're going to say that the pressure of the air, also sometimes referred to as P cylinder, and P atmosphere, is basically the corrected value. And there's an equation that allows you to do this correction. This is all also based on the ideal gas law, PV equals nRT. Now I rearranged this, okay? I rearranged this so that my N was by itself. And I'm also using the R value that takes into account my millimeters mercury as my pressure. So let me scroll down here a little bit and kind of show you how the data works. All right. So on the day that I pretended to do this data, which is actually really close to yesterday's data, I had 770 millimeters of mercury. I think I had 769 yesterday. And once I did the whole lab and then added the ice and got the smallest value for my 5 degrees Celsius, my little air bubble in the cold, chilly water was 3.5 mils. I also kind of ended up with a small H value when I did this. My value is probably smaller than what you're going to end up with. My H value was 21. So there's an equation in the handout that's loaded to Canvas that says take your pressure, so in this case it was 770, plus, okay, and treat this as if they were following the rules of order of operations, meaning that you need to multiply your H value times 1 over 13.6, because that's the way the equation works, before you add them together. So do the H times the 1 over 13.6 before you do the addition. Otherwise, you're going to end up with a really strange number. Your number should be somewhere in the neighborhood of the answer I got here. I got 71 and a half. Probably the lowest thing you're likely to get is maybe 761. You might get as high as 780, 785, because we're talking about millimeters of mercury. If you get numbers much higher, like in the thousands, you have math error, because that's not possible. So now we go back to the rearranged version of my PV equals nRT. I'm solving for my n, and I'm using the value of my cold one. The note, my parentheses say the corrected one. So once you have looked up your 5 degrees Celsius, or maybe even a little bit smaller, value of your air bubble, you have to subtract 0.2 of a milliliter before you crunch it into this equation. This is taking into account the fact that your meniscus is upside down. So instead of using 0.0035, I corrected it very slightly to 0.0033. So look at my data here. I've got P 771.54. I've got V, because remember this is in liters, 0.0033. My R value is the 62.371. And keep in mind that your temperature must be in Kelvin. 5 degrees Celsius plus 273 gives me 278. Everybody should probably end up with a number of moles, an n value, likely with a -4 exponent. If you had a really, really, really tiny air bubble, you might end up with 10 to the -5, but even that is kind of somewhat unlikely. If you do this math calculation and you do not end up with a negative exponent, you have made a math error. Keep that in mind. Now, you actually have to do it for all the other 6 data points too, okay? So after you do this first calculation, then ignore the 5 degrees Celsius one for the rest of the data. Keep your n value. Don't change your n value. Change your V's and change your T's. So if I look at where it says for other temps, at a warmer temperature of 328 Kelvin, I had an air bubble of 5.3. Well, actually, it was probably 5.5 with my correction. It's 5.3. And I put my data in, PV equals nRT. And first thing I do is crunch all of that. And what you're getting is P of air. Okay, that's what the equation tells you. And then you have to subtract. Take your original value there from the above calculation. In this case, it was 771. Subtract your P of air, and that will give you P of water. You will end up with 6 data points that look kind of like this. You're going to have natural log of those P water values. And then across the bottom, your x-axis is going to be 1 over T in Kelvin. You should end up with a negative slope. Use Excel to do your trend line because the slope affects being able to answer the remaining questions on your lab report. So this is, there's a version of this on Canvas, so you can go back and look at it again. And like I said, I'm taping this lecture, so you can also go back and re-listen to the explanation also. So some of you already done this, some of you will be doing this next week. But it's not an easy set of calculations. So that's why I wanted to spend a little bit of time talking about the math that's involved. You do need to use Excel to do your graph because otherwise you're not going to have a good trend line based upon your data. All right, so questions about the solution stuff that's supposed to be submitted tonight for homework? Okay, and then everybody needs to continue working on lab reports. Try not to get too far behind. I know it's hard with us only seeing each other like every couple of weeks. But hopefully try to keep up and keep submitting it. And somebody actually sent me a question. I glitched one of the, I think it was the spectroscopy one. Somehow or other, I had not set it to say yes to accept submission reports. So I think I fixed that now. Hopefully that's the only one I glitched on that. Like I said, this has been my chaos week for some reason. I'm not really sure why. I was doing pretty good the first month, and now my brain is kind of like run out of steam or something. Hopefully I get it all caught up here in the next couple of days. We will continue onward with kinetics, but Tuesday, we will go over solutions homework, and I will talk about your test. Your test will be set so that you should accomplish it between midnight on Thursday and midnight on Monday of next weekend. There'll be a 4-hour time block. Basically, once you start the timer, it cuts off after 4 hours. You don't have an unlimited amount of time, but 4 hours should be a really decent amount of time to even, sit and puzzle over something if you need to. Questions?
I do have one question.
Okay.
This spectroscopy lab in Canvas says it was due yesterday, but you did say we had until next week.
Oh, yeah. Okay. I have due dates set for lab reports just to try to poke everybody a little bit to not get behind. However, unlike homework for labs, as long as you get it turned in before hopefully way before the end of the semester, there's no penalty. It's just so that I can set Canvas so that everything has an actual due date.
Okay.
So yeah, if you turn in your spectroscopy anytime in the next couple of weeks, that's fine.
Okay, great. Thank you.
Like I said, I'm just trying to, because usually you're when I see everybody every week back in the distant past, usually they were due the week after we did the lab, but because we're on this weird 2-week rotation, yeah, I kind of threw that out the window. It just, I need grades eventually. Okay. So, like I said, try not to let yourself get too far behind, because I had 1 or 2 people last semester who did okay eventually, but they ended up sending me like 8 files like the week before final exams because they had kind of gotten behind on crunching their lab data. Just try not to let yourself get in that particular scenario, because it's kind of brain twisting if you have a whole lot of stuff that has to be crunched at once.
And I know I messaged you about the solutions pre-lab, and I was having trouble uploading it. It said I had exceeded the amount because I kept getting an error, but now it says it was successfully submitted. Could you check that for me and get back to me at some point and see if it's actually submitted properly? Because I can't see what I submitted.
Hang on, let me see if it'll let me reactivate that part of Canvas. And
it wasn't working when I was trying to do it, but now it says it submitted successfully. So I just don't know if it actually worked or not.
okay. Let's see. Let me see if I can view. Okay. This is for
Solutions pre-lab.
okay. So I have one person is listed as submission, and yeah, Holly,
Okay.
I
Yeah.
did get it.
Okay. I hope it's correct and not like corrupt or something.
No, I can view the file. So it's like 2 pages. So
Okay, great. Thank you.
that should be fine.
Okay.
Yeah, somebody implied to me that Canvas was being weirdly glitchy this afternoon. So, and I don't know if you guys noticed, there's this weird message, or at least I get a weird message that says SIS at like midnight on the 25th of February is undergoing a systems update, and there may be like intermittent downtimes that final weekend of the month. So kind of keep an eye on that. I'll let you know more if I find out some more info about that. But yeah, it's like it says something like you may or may not be able to access it between like the 25th and the 1st, which I thought was really bad planning because it's in the middle of the semester. But yeah, I didn't, not something I have a control over. But your test should be the weekend before that, so that should hopefully not be a problem. Other than that, email me if you get stuck, and yeah, keep an eye on Canvas. It's been a little flaky lately as far as like connectivity and issues. Otherwise, I will see most of see all my lecture people on Tuesday.